everybody. This is the third part of my presentation about indoor positioning systems. And for this last part, I am going to present you our project, which is built with a lab in Toulouse, another one in Valence, and with two companies which are Concept and Digichrome. So this project is called Cette, and it's an indoor location system using wireless radio systems. So let me recall you three types of application for indoor localization. So you can use it for commercial application, for firemen and military operation, and also for security in buildings. And if you want to use it as a navigation service, for example, so you have to deploy the access point inside the building, connected to electricity on wire network for long-term utilization. But when it's for fireman operation, for example, you cannot install your access point inside the building before to go inside. So you have to deploy your access point outside, near from the building, and it must be working without any wire. So you need to include batteries for short-term utilization, which is something like few hours. And finally, you have also this type of security application where you need to localize your own mobile, but also unknown mobile. So you need to do your localization function inside the infrastructure, not inside the devices, because with unregistered terminals, it's not possible to add some piece of software, of course. So how does it work? First, we have an absolute reference system composed of a set of beacons, access points, which are outside near the building, and it is working with absolute coordinates. So you need to have, you need to know where are precisely deployed these beacons, this architecture, because when you are going to measure some distances between this beacon and the mobile, when you have calculated this distance, you need then to calculate an absolute coordinate. So you need to have some repositories, in fact. So we use two different systems to calculate distances. One is about time of flight, and the other one is about signal strength reception. For the time of flight, we use the ultra-wideband and another new signal, which is LoRa with 2.4 GHz signals. For the signal strength, we use classical LoRa working at 868 MHz. And at the end, we need a fusion piece of software in order to combine all the data, in order to define the best confidence index on each values, in order to be sure that all the collected information tends to the same coordinates. So in the fireman context, the equipment is composed of beacons distributed outdoor, working on batteries or which are on board a drone, UAV. So we also have ultra-wideband component included inside the beacon, but it can be also components which are left inside the building, through the building. Okay, so we use these two distance measurements methods. One about time of flight and the other one about RSSI, signal strength reception. So the time of flight is interesting because it's accurate, but you cannot cross walls with this technique. And with signal strength, you are going to have less accuracy, but your signal can cross walls, and you have, of course, bigger coverage. So sometimes it's only possible to have signal strength measurements, and sometimes you have both. And when you have both, you can improve the accuracy of the calculation of the position inside the building. So how is working the beacon? So because we need absolute position, we need to have a GPS inside the beacon. Like this, we can have absolute coordinates, but we need to have in some way a very accurate position. So we have different possibilities, but mainly we use DGPS in order to have an improved position. Then we need to characterize the building, sending signals between each beacon in order to identify if the area is good for the signals or is very hard condition, which means there is a lot of walls between beacons. Like this, we can identify in advance what type of signal we are going to have when the mobile device will be inside the building. So when the mobile device is activated, it will receive LoRa signals, and this is the last step. We can compare the signals exchanged between the beacons and the signals exchanged between the beacon and the mobile device. And with this comparison, we can have a good accuracy. All the pseudo-range measurements on distances will be merged on a piece of software which is located on a Raspberry Pi, which has a Linux system embedded. So this is a graphical description of the system. So you can see that there is two types of lines, of arrows, green arrows and yellow arrows. So first of all, there is signals transmitted from each beacon to all of the other beacons in order to characterize the environment, the area, trying to define how many walls there is between each beacon in order to know if the area is easy or hard for signal transmission. So this allows to define if the area is what is the level of absorption in the area. Then when the fireman is inside the building, then it receives the signals from the beacon, and the fireman can compute on its Raspberry Pi its position inside the building. So this is the hardware components we are using. So in the center you can see the Raspberry Pi, which is connected to some devices such as the ultra-wideband component here, on the LoRa in this new configuration of 2.4 GHz. And finally, the classical LoRa component with the classical 868 MHz frequency, and at the end the DGPS here in order to have the absolute position. So the Raspberry Pi has its Raspberry 0, which can communicate using Wi-Fi 2.4, so you can manage it at some distance, and all the devices I explained. But we can also add SDR, which is software radio device, and thanks to this specific component we can have a lot of details about the reception. It's very interesting, very open environment in order to measure the reception signals. So, what type of software architecture we used? We took the choice of MQTT. MQTT is a software bus, which means message queue telemetry transport, and it's a protocol which is used in IoT, and we use it because it's well adapted with embedded system, and we use this protocol on its above TCP/IP. You need to define some topics, and you have a tree of topics you can define. A topic is in fact a variable, a value, and this value can be published on the bus and can be read, subscribe on the bus in order to exchange some information produced by some devices, and then you can consume this information on your piece of software in order to read, to have some input on your program. So now, how can we use this drone in such type of application? So we are going to define some objective to automatically deploy the drone on the area near the building. So sometimes it's very difficult to go near from the building all over the building. So probably sometimes it's easier to send drones, and it's also probably faster. So the drone carries GPS LoRa beacon in order to be near from the building. We have a remote control of the drone. That means we can prepare the trajectory, send the trajectory to the drone, and ask them to go directly to the final point. We can define several types of trajectories or trip, because it can depend on the situation. So Sometimes you need to be very fast, sometimes you need to be safer, etc. So for the emergency, if you want to have very short time and you want to be really quick, you are going to define trajectory through the building, all over the building, just because it is the shortest path on the if it is possible, if only if there is a good condition, if there is a fire on the roof of the building, probably it's not a good idea to go through. So if you want to have a safe trajectory, what is the best solution is to define a common circular path all over the building in order to go on the final position. And if you want to do something which is some stealthy, you need to be very quiet, you need to be discreet, probably because the drones make noise. You need to have a long distance between the drone and the target building. So let's have a view. How can we define the drone trajectories? So if you want to deploy, let's say in this example it's six drones. So you want to put one drone on the top of the building, on it's fine, on four on each side of the building. So you need to define a specific trajectory for each drone. So this scenario is good for the time. You can save some time, but if there is smoke or fire on the building, probably it's a little bit risky, and it takes some time to prepare the trips because it's a different trip for each drone. This is the example for a secure or safe scenario. So that means you have only something like one trip, and your drone are going to do part of this trip according to the location. So the main drawback is that you mean some delay to deploy your drone because it's not direct trajectory. Here you can also do something which is probably interesting. You can do some cross flight in order to scan the building. If you have two drones, you can turn around the building in the opposite way in order to send some exchange, to exchange some signals in order to define if the building is good or not for transmitting signals. But at the end, if you do in such way, the characterization of the building will be harder to achieve. And if you want to have a stealth scenario which is furtive, so you need to have a quiet travel, low speed, on long distance. You have to put more distance between the drone and the building, so it takes a long time to implement. It's difficult to have a long trip for a drone, and of course at the end the accuracy of the localization will be less accurate, of course. So what type of drone are we using? In fact, we use DJI Spark drone UAV. So it's quite small. You can add a little bit of payload some little bit of hardware. And of course, if you want to do some practice with the drone, you need to respect the French regulation. Probably you need to have a professional use of this type of drone, because you are inside the city or near a building. So this is some information about the French regulation. So if the overall drone is weighted less than 800 grams, you don't have to register your UAV. But if it's more, you need to have a registered UAV with a number, with an ID. So on cities, of course, you cannot use drone without professional license. And if you want to fly during night, you need to have a special accreditation to do that. And the last point is if you are out of sight of the drone, it's possible in a professional way, but you need to have 2 pilots, one in each position, in order to have a full view of the drone from the beginning to the end. So this is a short list of few drones which are compared. So it's something like price between 500 and 1,000 euros. So you have various speeds. You have time of flight which are different from 15 minutes to 30. But you have also distance of control, of remote control, which is different. So something like between few hundred meters to 4 or 5 kilometers. Of course, if it's in view. So what is interesting also is there is an open SDK that can help you in adding piece of software to drive your drone. So what about the stability, the quality of flight? So sometimes for 500 euro, it's something like correct, but sometimes it's the domain of usability is not very important. When there is some wind, when there is some rain, the flight will be very bad. But for the DJI Mavic Pro, I can see that there is a very good characteristic of flight. It's very stable. So even if there is some wind, even if there is some rain, this drone can work very accurately. So let's go back to the DGPS. It's just a recall. You need to have a base which is sending some information to the rovers. In this example, in this picture, there is only one. The base has its own physical coordinates. It is manually done, or it is post-processed, let's say. And then this coordinates is compared with the satellite signals received, the computed coordinates, and then it compares the real coordinates with the calculated coordinates, and it can send then some correction in order to add or substitute some little bit of time in order to improve the accuracy. And it sends this correction over a network, a wireless network. It can be Wi-Fi, but it can be also LoRa. We can use LoRa because LoRa has enough throughput, enough speed to transmit the information to the rovers. So I already show you this piece of software. So it's a view with information sent by the base station for the GPS. And then this is the view for the rover. And finally, this is the LoRa component. This LoRa component is a LoRa chipset for wireless communication, and it is also on the green part here. Here is the LoRa chipset, and then there is also a microcontroller, which is an RM M0 here, and you have a small antenna, a wired antenna here. On the other antenna is a little bit better for transmitting and receiving. And thanks to this component, you can use frequencies like 868 for Europe or 915 for the US. So what is interesting with LoRa is that you can evaluate the temporal stability of the measurements even in heterogeneous environment. It's finally more stable than the Wi-Fi signals, and there is also some properties to cross concrete walls, buildings, even in basement. So it's really a good signal, a good simple signal to exchange measurements inside the building. And the software is developed using the IDE of Arduino, and it's very simple to use it, very simple to flash the program on the microcontroller. And we are going to use this component for practices. We are going to use practices on the middle of June, and you are going to develop some program for this platform. So in order to have an idea why LoRa signal is better than Wi-Fi on such application, because the reception threshold is very, very different. For Wi-Fi, it's minus 100 dBm, and for LoRa signals, it is 100 on the minus 130, 35. So let's say when you have 3 dBm of difference, the signals is twice smaller. So here there is 35 of difference. So it's very, very different. Why is it so different? It's because the LoRa signal is a simple signal. Wi-Fi is a really very complex signal, very rich, because we want with Wi-Fi to have a lot of throughput. We want to have a lot of bytes per second. So if you want to have such characteristics, your signal is very complex, and it's very difficult to listen if there is a long distance. At the opposite, for LoRa, it's really simple. You don't have a lot of throughput. You cannot send a lot of bytes per second, but you can, because the signal is really easier to understand, you can receive it even if there is a long distance. Okay, so if you can see on the draw here, inside the building, Wi-Fi is something like under 100 dBm at something like 50, 60 meters inside the building. Then you cannot receive anything. With LoRa, it's nearly the same, as you can see, but the threshold is less, is very different. So at the end, you can receive the LoRa signal at something like 1 kilometer, even if you are inside the building. On the other two curves is a comparison between outdoor with Wi-Fi on LoRa, and with Wi-Fi you can expect something like 300-400 meters outside, but with LoRa it's better for you have a better signal for the same distances, but because the threshold is very low, even if there is 4 kilometers, you still receive the signal, and you can go up to something like 10-12 kilometers of distance, of coverage. So this is why the LoRa signal is very interesting, because it's a simple it is a simple signal. You can here receive the signal from a longer distance, and thanks to this technology, you can send, exchange data with two LoRa modules with a very long distance. So now, what about the geometric method? Because when you receive some signals, RSSI or time of flight or things like that, at the end you need to define coordinates. So you have to transform the electromagnetic information, and then you have to compute coordinates. So in order to do that, you have to define if you are on line of sight or non-line of sight. It must working on both. Then, for example, we use the Friis formula, but we modify this Friis formula in order to take the environment into account. Because when you exchange information between access point 1 and 3, or access point 1 on 2, or access point 2 on 3, you are going to have some values about the characteristics on the environment here. So because you know the distance, because you know the signal strength of the reception, then you can define a coefficient for the environment, which called it E. And then in the second step, you have the coefficient here, which is specific for each couple of access points. And when you want to define where you are with your mobile, then you can measure some distance using the Friis formula, and the distance is D. So this is our method. Our method is, instead of doing the intersection of 3 circles, we prefer to use 3 bisectors. And here we have a perpendicular line on the line BD here, and it's closer from B than C, because the signal in B is better than in C. So this B sector is weighted according to the signal strength received on the mobile device. And then when you cross these three bisector, so you have a small triangle or a big triangle, depends of the accuracy of your signal strength. And if the perimeter or the area of the triangle is small, this means you have a good chance to have a good confidence in the results. And if the triangle is bigger, perimeter or the area, probably you have less confidence in the results. So when you want to monitor or supervise your operation, you need to prepare something on a map. So this is an example of doing such work. So you want to go inside this building. Okay, let's deploy some beacon around the building, and then you can go inside. And when you are inside, we are going to give your indoor position. And you can, like this, you can manage to visualize the results easily. If you use drone, of course, you need to prepare the trajectory, for example, using this interface in order to have the right position at the end for each drone. So let's conclude this presentation. Everybody can see that LoRa communication, wireless communication, is really interesting for such application. You can have very long distance, but in building, of course, you have shorter distances because you have non-line of sight communication, but it's one of the best signal to cross walls, even some levels or including basement, using very low power consumption. This is very important because if you want to have an infrastructure which is working for 10 hours, it's better to have very low consumption because we need to have small batteries, less wet. Like this, it's easier to put it all over the building. And if you want to put it on a drone, you have to be, you need to be low in power consumption. So we can see that LoRa technology for such application is much better than Wi-Fi or low energy Bluetooth. Low energy Bluetooth is for very short distance, and Wi-Fi is a too complex signal with too much throughput bit per second in order to be usable in hard environment. So the characteristics of LoRa is because it's a simple signal, is very stable. The measurements are constant over time when there is no modification in the environment. So this is quite important because, for example, compared to Wi-Fi, which is a very complex signal with subcarrier, for example, on the FDM technology, which is orthogonal frequency. Of course, there is easily multipass on such signals. On LoRa, it's more one pass or few passes, and it's always same power on each pass. So this is why LoRa is a very interesting technology for such application. So thank you for listening, and now we are going to have some exercises next, and we will conclude with practical exercises programming LoRa component using Arduino IDE. Thank you. Bye bye.